Okay, time to get going. So let's see here. Picking up with a new topic. Well, kind of a new topic. This is still in the section on change of variables. Again, monster section. Enormous, huge section. And this is beginning the part of the section that I think a pretty strong argument can be made should be its own section. But it also does make sense to have it in the same section because this is really a special case of change of variables. It turns out there are particular specific change of variables functions that are used extremely often. So often that we have kind of a method for how to think about these very specific change of variables functions that we're going to be using over and over again just to streamline the process so we can do it as efficiently as possible. And here they are. The first one is the polar coordinates change of variables function. Now, you may recall when we talked about polar coordinates long ago, I made this statement that it's most naturally thought of as a function, right? Very often we think of polar coordinates as being just kind of a different sort of rules for how to identify where you are in space, and that's fine, I suppose, in a lot of circumstances, but arguably a little bit, there's a bunch of seemingly arbitrary rules that you have to come up with in order to make that make sense. And it's really much more graceful, I think, to just say, yeah, it's a function, here's the formulas, right? And then you can, from this, as a fundamental, then interpret, how do you visualize that geometrically? So anyway, this function, the polar coordinates change of variables function, change of coordinates function, is a fantastic change of variables function. And so we can view x and y as functions of these two new variables, r and theta, and then we can talk about the process of taking an integral over here and pulling back to an integral over there on a different domain, the pullback domain. Okay, all right, so now in order to do this, we need to know what the stretching factor is. Most of the work of the stretching factor is computing this thing, this determinant. Everyone should do this once in their lives. Your turn. It won't take you very long. It's maybe a 1-minute calculation. Give it a shot. Make sure you can do it. The answer is R. Okay. All right. Likewise, very analogously, the cylindrical coordinates, change of coordinates function, is a fantastic change of variables function in a lot of circumstances. Its Jacobian determinant is, again, another calculation everyone should do once in their lives. And again, your turn. So probably also about a 1-minute calculation. It's not so bad. Make sure you can do this. Answer is R. Make sure you get the right answer there. And then spherical coordinates. Same deal, right? We think of this, again, as a way to convert spherical coordinates to rectangular coordinates, but very naturally, in this case, we're going to view it as a function that serves lovely as a change of variables function through which we can do pullbacks. Again, we need to compute the Jacobian determinant. Again, your turn, right? Make sure you can do this. Now, this one's a little harder. This one has a little tedium to it. It's not so bad. It'll probably take you 3 to 5 minutes. Right? But it's a good exercise, and again, everyone should do this once in their lives, so please do give that a shot. Here's what the answer is: rho squared sine phi. That's going to be important to know. Okay, now it is tempting to say that we now have our stretching factors and we can just proceed. It's not quite true. What we've computed here as our Jacobian determinants, right? That's just the thing whose absolute value is the stretching factor. Don't forget this absolute value. It's very important. Really makes a big difference. Minus signs matter. Right? I mean, again, it's not a question of how close cosmetically is your answer to the right answer. The question is, did your bridge fall down? Right? So we got to worry about that. Okay, how are we going to deal with the fact that we have these absolute values in there? Don't forget, stretching factors go into our new integrand. Absolute values in your integrand is a problem. But none of our shortcut formulas for antiderivatives work with absolute values. We don't like the fact that there's absolute values here. What can we do about it? And there's a lovely little workaround that has been noticed, right? It's easy to notice, and that is if you choose. If and choose, I emphasize, right? There is no law that says that you must choose this. I think it's highly advisable to choose this. I'm going to practically insist on it, but not quite. But again, this is a choice. This is not a dictate. Just choose to always look at positive values of R. Choose never to allow negative values of R. Well, if you make that choice, this thing that you're taking the absolute value of is positive. Its absolute value is itself. And you can throw away the absolute values. So that's the clever little move. And by the way, this is why a lot of people, a lot of instructors, I'll say, will insist from the very beginning that polar coordinates only works when R is positive. Nonsense. These formulas work just fine. No problem. When R is negative. All good. Not an issue. It's only when you want to get rid of these absolute values that you've got to insist now that R's got to be positive. Otherwise, you cannot get rid of the absolute values. Okay, so again, we make that choice for selfish reasons. So change of variables works out better. Likewise, here, we're going to choose R to be positive, again, so that we can get rid of the absolute values. Works exactly the same in cylindrical as it does in polar. Now, here's where things get a little different. Again, a lot of people mistakenly think that spherical coordinates is just like polar coordinates, just micro differences, but it's morally the same. And in particular, a lot of people think that rho is basically just like R, and it's just slightly different. And again, importantly, it's not, because while R is the thing that you have to insist on being positive in order to lose these absolute values, that does not work at all in this situation. If you need to get rid of these absolute values, if you want to ensure that this Jacobian determinant is always positive, it doesn't help you a bit to make constraints on rho. Insisting that rho be positive doesn't do a thing, right? Okay, because it's, for one thing, it's going to be squared anyway. It's never negative. Rho squared is never negative. It's just not a problem. That's not the problem. The problem is with the sine phi. That's the thing we need to worry about. And in order to make that something that we can deal with in a convenient way, we're going to make this choice right here. We're going to insist that phi be between 0 and pi. That will ensure that sine phi is never negative. And then I can get rid of those absolute values. And again, life is good and we can do calculations. Is everybody on board? Okay. All right. So that's what you got to watch out for. Now, by the way, how do we feel about the fact that we have now tied our own hands in this way, and we're no longer allowing ourselves to think of phi as anything other than between 0 and pi? Is that going to be a problem? No, not at all. In fact, this is awfully convenient. If you think about it, again, phi is the angle off of the z-axis, the positive part of the z-axis, and the easiest way to think of it, the most natural and convenient and intuitive way to think about it, is to have it be between 0 and pi. These are the preferred, intuitively, geometrically convenient preferred values of phi anyway. So if you make a promise to always do things the easiest possible way, then you get the additional advantage of the absolute values disappearing. Does that make sense to everybody? All good news. This is a win-win. Okay. All right, so now let's do one. Here is my first example, and we're going to start off working a question where we have this integral to be defined on this domain here, specifically the first quadrant portion of the unit disk is our domain. And now let's just speculate, how is this going to work out if we do this in rectangular coordinates, if we do this the only way we've previously discussed, namely slice it up. Well, here's what your bounds end up being. And by the way, if you do it dx dy instead of dy dx, it's not that different. You're still going to have a square root in your inner bounds, which means you're going to have a square root in your outer integrand, which means you're going to be doing trig substitutions and other tedious, doable. It's doable. It's not that it's not possible, but it's an inconvenient computation. Everybody see why this is undesirable? Okay. All right, so no fun there. So I claim, though, and this is a pretty cool observation, I claim that is exactly the image of this rectangle right here by way of the polar coordinates change of variables function. And how do I know that? Well, it's kind of think some things through here. Let's look at this edge right there. That edge, you can see, is on phi equals 0, where r goes between 0 and 1. Now just think about polar coordinates, and what do polar coordinates look like in the xy plane? That looks like that edge right there. And now just moving around, let's think about, color choices. I'll use dark blue. That edge is where r equals 1. So put us on the unit circle over here. R equals 1 between theta equals 0 and theta equals pi over 2. And, well, that puts us about like that. Right, you can keep working your way around. This edge is that. And then lastly, this edge, this is the weird one, this red edge over here, this entire edge is on r equals 0. That entire edge gets pinched down to just that single point right there. Everybody happy with that so far? So, all right, now let's think about the insides. Let's look at these kind of little, what you might call theta slices. These are eventually going to be theta slices. What do those look like? Well, each one of those represents a constant value of theta, r ranging between 0 and 1, which is going to be kind of like this. So I think it's pretty clear at this point that the image of this rectangle is this quarter disk. And so we have ourselves a situation where we can do change of variables. Everybody happy? All right, so pulling back. Let's see here, delete. So we have x squared plus y squared becomes r squared. That's just plugging in. That's just, don't forget the relationship between x and y and r and theta. Nothing to that part, right? dA representing pieces of area in the xy plane, stretching factor times dr d theta. We've already computed our stretching factor as r. Don't forget to include that stretching factor. Super easy to forget, right? So make sure you put that in there. The only thing that remains is to indicate the bounds on our pullback domain. Our pullback domain is a rectangle. Boom. There's the bounds. You've got to love rectangles, and we're in business. We have successfully now turned our undesirable integral over here into a new, highly desirable integral here. Look how easy it is to do the calculation. Altogether, my integrand is just r cubed. That has an easy antiderivative. That results in a single variable integral here that is super easy. We're done. We win. No trig substitutions, no nasty algebra. Everybody happy? Okay. So this is a fantastic change of variables function. We're going to be using it a lot. As you might imagine, the world's full of circles. When you're dealing with a circle, polar coordinates is desirable because that circle turns into a line, which we like much better. That's basically the main reason that this works out so nicely. Okay, now here is a different take. By the way, this is, in some sense, depending on how you think about it, everything you need to know. You can, in fact, I suppose, constantly do it exactly like this, and that will work. But there's a much easier way to think about this whole thing, and that is to point out that when you take your pullback domain, and let me draw my pullback domain again, maybe it's some rectangle like in the last example. When you look at your pullback domain, you're going to be slicing it up. You'll be doing theta slices, like so, R slices of those theta slices, perhaps, like so. And here's the thing, these slices, you can straight up see them in the XY plane. Right? All of these various theta slices are just in the theta direction are just rays coming out of the origin in the XY plane, like that. So a case can be made, I think this is a pretty good case, that rather than take your existing domain that you're looking at, reverse engineer to figure out what the pullback domain actually looks like, only to then slice it up, just notice all these slices, you can see them right here on your existing domain. Just realize these rays coming out of the origin, this is what theta slices look like in the XY plane. So we don't really even need to draw the pullback domain. We just need to represent what it looks like to slice it up. And what it looks like to slice it up is this. So just do this. Don't even think about that, at least not geometrically. So let me show you an example of this in action. Here's that same example that we were just doing. Right, so we were looking at this integral on the domain being this quarter unit disk. Highly undesirable. Algebra works out terrible. We don't like it. We're trying to avoid having to deal with that nonsense. So, all right, let's do this using polar coordinates as a change of variables function. We're just not going to draw the pullback. Now, we've already agreed there's the pullback, right? But we're not going to look at that. We know it's there. We know there's some domain. We know we're going to be slicing it up. And I can just see what those slices look like over here. So when I get to the point where I'm thinking about the range of values of theta, how do I know it's 0 to pi? Well, because this is what theta slices look like. There's the first one. Yeah, technically that's this slice right here. I don't need to see it over there, though I can see it right here. And I can see it in the XY plane using my already pre-existing geometric familiarity with polar coordinates. This is what theta equals 0 looks like. So, no problem. Continued slices. Continued slices. Where's my last slice? Well, I can see it right here, my last slice. Right there. That's where that's the last slice of my area, my domain, until I'm done. And I can see right there that it's pi over 2. Now, okay, to be fair, yes, I can also see it over here in the r theta plane. Yeah, I guess. Right? But I mean, I didn't want to have to think through what this domain looks like only for the luxury of being able to see theta slices looking like I'm sort of accustomed. I can just remember that they look like this right here. And it's much easier to just see that is that last theta slice, pi over 2. And thus my bound 0 to pi over 2. Everybody on board? All right, now, continuing. Let's pick a value of theta. Let's pick a value of theta. And remember, now there is my theta, arbitrary theta slice. And yeah, I suppose I could think of it over there too. The starting value of r, where does r start? Well, it starts right there where, again, using my pre-existing familiarity with polar coordinates, it's r equals 0. You can see it right there in the XY plane picture. It's the origin. R is 0 there. Okay, sure, if you insist on visualizing it over here in the r theta plane, yeah, sure, it's on the line that is r equals 0. You can think of it that way too, but it's harder to have to, again, generate the pullback domain when you can see what you need right here. Likewise, the n. Okay, so and then r equals 0. Whoops, wrong one. Sorry. R equals 0 is my lower bound. We're going to be done when r is at that point, which is on that curve, which has that equation, r equals 1. Again, pre-existing geometric intuition for polar coordinates. Much easier to see like this, I think, as opposed to having to look back over to here to identify that point, to have sort of interpreted that edge as being that edge, only to come to the same conclusion that r equals 1. Everybody on board? So this point of view where we sort of make this conscious point to don't think about the pullback, right? Yes, there's a pullback. Yes, we're doing change of variables. Don't forget your stretching factor. Very, very important. You're going to get a dramatically, hilariously wrong answer if you forget that stretching factor. Just don't look at it that way. Just look at it as slice up with what I like to call polar slices. Don't forget your stretching factor and knock yourself out. That's all it is. Okay. All right. So here's another one. Now the specifics of this example are pretty straightforward. You're going to notice first off, the easy part, that is just r, nothing to it. dA, dx, dy is just r dr d theta, because again, I know the stretching factor is r, established previously. So all that we really have left to do here, the only part that's geometrically challenging, is to figure out the bounds. And now you can take this domain, this unit disk, and you could try to draw the pullback in the r theta plane, and it's perfectly doable. It's really no problem. But again, you don't need to. So much easier just to say, all right, well, look, I'm going to be slicing this up with theta slices. Theta slices look kind of like this. And I can see from the picture that theta starts at 0. And then theta goes all the way around. I can just imagine these theta slices continuing as I go counterclockwise around there until I end with this last slice, which I will have gotten to by theta increasing by a full 2 pi, thus ending me at theta equals 2 pi. Is that cool? So a nice little easy way to remember this is just whenever your theta goes all the way around, right? You might say this, whenever your domain surrounds the origin. Right? It's just a different way to think about it. Theta is going to go all the way around. Then theta goes from 0 to 2 pi. All good? All righty. Good little trick to remember. But make sure to check all these details, by the way. Good exercise. Okay, a couple of tips. These are not laws. These are just things to make your life easier. I have found through experience that in practically every case, practically all cases, this is at least as good as the other option. In most cases, it is the better option. Sometimes it's a draw. Sometimes you can go either way. But just for the convenience and the consistency advantages, just so that geometric slicing process will always look the same in your mind, and because the counterexamples are so rare and highly manufactured and unnatural, I've never seen a counterexample to this statement arise, organically in a real circumstance. Always do dr d theta. Don't ever do d theta dr. It's almost unheard of to be advantageous. So don't waste any time thinking about the other slicing order. So again, makes your life easier. This next one is also just a little bit of advice. There is a real problem. I've been teaching multivariable for a lot of years now, right? And I have noticed over and over and over again, it happens so often, and it makes me cry a little bit every time. And students will just forget the R. Now let's think about what are the consequences of forgetting that R aside from it being a mistake, and you get you get the wrong integral and therefore a wrong answer. Your bridge falls down, of course. But what do I as a grader have to make of this? Right? I can't assume that was just an inadvertent error. If the stretching factor is not in there, the work I'm looking at then shows no evidence that the student understands the idea of stretching factors. That's a real problem, right? That's arguably where all the multivariable calculus is. Everything else is trig and geometry, right? That's where the multivariable calculus is. This is a course in multivariable calculus. Oh my God, so problematic to forget that stretching factor, right? Does that make sense? So how can we cut down on what I am willing to bet is, in most cases, just an inadvertent oops on the part of the student? Well, my little ritual that I've come up with, and by the way, I do this for myself because I too am forgetful. I do not trust myself to remember things. It's so easy to get distracted. I always write this whole thing down all at once. I don't ever write down dr d theta without preceding it as r dr d theta. That's just a little, again, my little ritual. And I haven't forgotten my stretching factor in a long time as a consequence. At least that I've discovered yet. If you find one in the notes, please let me know. We're going to get that fixed. But I think I've been pretty good about it. This was very helpful to me. I think it'll be very helpful to you as well. I urge you to follow this rule. Don't ever write down dr d theta by itself without preceding it with r dr d theta. And now you've already gotten your points, right? The mere inclusion of this factor of r, boom, points. Get those points. Get that, on your score sheet. Don't just trust yourself to remember, oh yeah, I'll remember to get those points later. No, get those points immediately. Does that make sense? I'm convinced what happens is students will look at a question like this and they'll get bogged down in the geometry thinking about the bounds. They're like, okay, theta, okay, how's the slicing, blah, blah. Let me just write down dr d theta real quick to because as a reminder of which bounds I'm doing in which order, and I'll remember that stretching factor later. And then they're thinking about the slicing and the blah, blah, and the equations up, and then they just straight out forget that stretching factor. Don't let that be you. Okay. And then just a doff of the cap to what we already know. When you're interested in bounds, that comes from identifying the key points. Those points will be on certain curves. Those curves will have certain equations in which you can solve for the bounds. Okay, just like every other slicing process we've done. All right, here's a nice example. Let's suppose here that our domain is what we call an annulus. It's a ring sort of kind of thing, about like this. I don't know why, but I like to think of this as a moat around a castle on the little island in the middle. Whatever. So that's our domain. And the function that we want to do an integral of is this right here, and we have to recognize now that's there's a denominator problem here. You're not allowed to divide by 0, and if that denominator is 0, this thing explodes in a fiery ball of flames, right? And that happens at the origin. So this integral, perfectly well defined. No problem. This integrand is perfectly continuous everywhere on our domain. The explosion happens outside of our domain, doesn't affect us at all. Okay, that said, here's what a lot of students like to do to compute this, and that is to say, okay, well, I'll compute the integral on the entire disk, and then I will subtract what I get on just the sort of the island part, the island disk, and I'll do the green integral minus the purple integral, and that'll give me what I want. And the problem is neither one of these integrals is defined. This is all meaningless nonsense. Right? Strict rule, if you're going to define an integral, your integrand's got to be continuous as far as this class is concerned. That make sense? So this is a dead-in-the-water approach. It does not work, doesn't make any sense at all. All right, so another thing you could try, right? You can avoid that singularity by breaking this up into 4 separate pieces. And so you can, do it on that piece, and then on that piece, and then, color choices, on that piece, and then on that piece. And you can do this with 4 separate integrals, but your bounds have square roots in them. Again, highly undesirable. I don't advise doing it this way either. Yeah. Look how easy it is in polar coordinates. Theta starts there, goes all the way around, ends there, 0 to 2 pi. Theta bounds are 0 to 2 pi, nothing to it. For any given value of theta, my theta slice is actually something like that. The lower bound for r is going to come from this point, which is on that curve, which has that equation in which I solve for r, because I'm looking for an r bound, and solving for r, I get 1. Right? And then my upper bound for r going to come from that point, which is on that curve, which has that equation in which I solve for r, and I get 2. Everybody happy? Now, you can't tell the order that I wrote things down in this example, but I promise I did write down the RD theta all at the same time. Right? Again, make sure not to forget that R. Huge deal. Free money. Don't leave free money on the table. Right? Free points. All you got to do is write down R. In fact, I tell you what. In the past, I've had exam questions that were, do the following integral in polar coordinates. Maybe I just said do the following integral, and the right answer was to do it in polar coordinates. It's the best way to do it. And page almost entirely blank, right? The student wrote down only RD theta. I think that student probably got like 3 or 4 points, right? I mean, it's free points. Get those points, right? Because that R means something, right? That's important. So, again, make sure to do that. Okay, is everybody happy on this example? Okay. All right, now here's one that's a little tricky, a little geometrically tricky. Same process, right? We've seen how this process goes down a couple times. Let's introduce some algebraic inconvenience and some geometric inconvenience, by the way. Now, you'll notice our domain starts with this disk. And then we're going to exclude all of the points in our green disk that are in the red disk. So we're going to chop off all of the red parts that overlap with the green parts. And so all together then, a little geometric intuition, the actual domain is this kind of, it's like a solar eclipse kind of looking shape. Does that make sense? Okay. All right. So there's just a couple of little bits to this that I think are interesting. First of all, when you do your slicing, here's a mistake a lot of students make. A lot of students and this is, I get the source of confusion on this. It's understandable, but it's a mistake that students will very often think of theta slices as emanating out of the center of whatever round thing they might happen to be looking at, and will think of their theta slices like that. That is, of course, nonsense. Theta slices always come out of the origin, not the center of whatever round thing might be looking at you. So heads up about that. I mean, I know students don't consciously think that, but again, when you write answers down as if that's what you were thinking, it's just easy to make that mistake. Okay, so theta slices come out of the origin. This, then, is what theta slices look like so. Everybody happy with that? A little weird to draw. And we can then think about first and last, and the first slice is down here and the last slice is up there. So let's talk about how are we going to figure out what the value of theta is on that first slice. Let's just focus on the first slice here. And well, I'm interested in computing basically this angle right there. I can see theta 1 is going to be negative just from where it is. But how am I going to figure out that angle? The clever observation is to notice that that and that are both radii of what we know to be a circle of radius 1. And this is a radius of that which I know to be a circle of radius 1. And therefore, I'm looking at this little triangle right here, and this is clearly an equilateral triangle, and I've already, I took geometry in high school, and I know that these angles are pi over 3. Does that make sense? It's a real slick move. I wish I thought of it. I didn't. Somebody showed me this. It's a clever idea. But always be on the lookout for this. You'd be surprised how often it comes up that there are little hidden geometric conveniences that'll save you a bunch of trouble. Now, if you want to, you could... Not that there's anything wrong with this. You could say, all right, well, the point I'm interested in is on this curve with that equation, and it's also on this curve with that equation, and being as this point is on both of these curves, I could then solve for theta, do a little bit of algebra. It's not even that bad, and then thinking about the resulting choices, you get the same answer. But it's just a little slicker and a little faster, a little bit more reliable, I think, to make the equilateral triangle observation. Is everybody on board? Everybody's happy? I mean, again, pausing for questions if anybody. Alrighty, let's see now, how do I find my R bounds? So as per usual, I'm going to fix a arbitrary theta slice. I'm going to notice that R starts at that point, which is on that curve, which has that equation in which I solve for R, and I get 1. Right? And then what is the upper bound for R? Well, the upper bound for R is going to be at that point, which is on that curve, which, okay, now we have a problem. Well, I've already made a reference to this, but this curve comes to me in a rectangular form, right? The equation that comes from this inequality, because we're on the boundary of that disk. And that's in rectangular form, but I need to solve for R. So this is a situation where you've got to take an equation that you know in rectangular form, and you've got to convert it to polar. And so you just got to take that, convert down to that. That's a chapter 1 thing. We talked about how to do that in chapter 1. So make sure you can do that. That's going to be a skill that's going to be critical in doing these kinds of intervals. And so with that done, now reminder, ending value of R comes from that point, which is on that curve, which I now see has that equation. Solve for R. And there you go. Everybody happy? Okay. Cool. All righty. Okay, so moving along. Now this last one, this is a weird one. This is a singular calculation. This is a calculation of arguably kind of historical interest. This first got done a couple hundred years ago. I don't remember the exact dates, but it's really tricky and clever. And the question that we face is actually how to compute a single variable integral, which doesn't seem like it should have anything to do with multivariable calculus, does it? Where this integral comes from, now you may recall this e to the negative x squared function is important in statistics and probability, right? This is the form of what they call a normal distribution, which is extremely important. I don't know how else to say it. It's of fundamental importance in statistics and probability, right? And we compute probabilities with integrals. This is a very important integral to be able to do. And you can't write down an antiderivative in closed form, and so the fundamental theorem of calculus doesn't help. There's a problem, right? So here's the clever move. Oh my gosh, so clever. Super clever. First realization. This is in fact just a number. It's just a number. I don't know what number it is, but that's not a function. That does not depend on x. That's just a number. I'm going to call it j, but it's just some value that I just don't happen to know. Right? The role that x plays in the expression for this number is what we call dummy variable. It's just a placeholder. The value doesn't depend on, okay, well, wait a minute, but which letter of the alphabet are we using here, right? I mean, it's just a placeholder. It's going to represent the ranging of the values of the input to this function, and then I'm going to add up a Riemann sum. It doesn't actually matter. So if I were to multiply this integral by that integral, well, they're the same integral. Different dummy variables, but they're the same integral. These two have the same value. That's just j squared. No big deal. Proceeding along, this being a constant, I can factor it in to that y integral. Perfectly legal. It's just a number. Multiplicative constants move in and out of integrals, no problem. Okay. This integral, x is my only variable, y being further to the outside is a constant. That means e to the y squared here, e to the minus y squared, is a constant. And I can move that inside of the green integral. Right? This is a weird argument. I'm going to grant you that. Right? But it's okay. I mean, it's legal. We can do this. So that gives me a new integrand. I have now apparently an iterated double integral. My integrand is the product there, which of course a little bit of algebra shows me to be that. This being an iterated integral, I can reinterpret it as a double integral. X and y ranging over all possible values means I'm going to be doing this double integral over the entirety of R2. So what we have done to this point right here is we have taken a question that we don't know how to solve, and we have successfully turned it into a harder problem, seemingly. Right? And you'd be surprised how often in math it works out that the best way to solve a problem is to first turn it into a harder problem. Weirdly, sometimes you get lucky and things turn out nicely. So again, having gotten down to this point, what do we do here? The slick move. And the reason that I'm showing you this in the section on polar coordinates is because if you just rewrite this in polar coordinates, and that's all I did. I just rewrote in polar coordinates. See, dA, rdr d theta. Think about the bounds, of course, also. And now if I look at this inside integral, that inside integral is super convenient because that stretching factor is exactly what I need to make the substitution u equals negative r squared. A couple of constants show up here and there. And easy integrals, don't forget the improper integral, limit to infinity, etc. Basically, it turns into an easy single variable calculus problem that I'm going to suggest y'all fill in the blanks of yourself. And again, good exercise. I hope you do it. You get pi. We recall, of course, that this was the result of computing j squared. So j is the square root of pi. Super clever calculation. Everybody happy? Okay. All right, now as we discussed earlier, cylindrical coordinates breaks down kind of like polar coordinates does. Again, you can think of the conversion formulas as a change of variables function. We've already computed the stretching factor. We've already made the promise that henceforth, so that we can avoid absolute values, we'll always choose non-negative values of r. All that's, we've already established. We just have to think about, well, what do these slices look like in XYZ space? And the most important one is to think about theta slices. Constant value of theta. There is a theta slice representing a constant value of theta. What does that look like in the XYZ space? Well, here's a constant value of theta in XYZ space. So this is what theta slices look like when you're using cylindrical coordinates. They're just planes, half planes. Or it's got to be positive, right? Half planes hinged on the z-axis. So that's all you got to remember. And then, you can think about r slices. It's going to turn out not to be a problem. And you can think about z slices. Well, of course, we already know what z slices look like. Certain tips and tricks. Again, it's going to turn out that of our 6 options, you'll never need to use anything other than these 2. There is no organic example that I'm aware of a situation where there is a slicing option that is better than at least one of these 2. So just always use these 2. And the way you remember these 2 options are that r and theta are always together and in that particular order, right? Always dr d theta, always keep them together. And then the only question is whether dz is further to the outside or further to the inside. That's the only thing you got to remember, right? So those are your only reasonable options to think about. I'm going to make the same sort of strategic advice that I made before. Always include your r as you write down those differentials, whichever of these differentials you're using. Don't ever write dr d theta dz by itself. Why would you do that? Oh my God, you're just setting yourself up to forget and just lose several points, possibly conceivably as many as 5 points or something. For why? Why would you take that risk, right? Just write this down all at once. Now you got those points in the bag. Much safer. And then again, same sort of slicing process we've already talked about. So let's see here. We can do one of these next examples here. Again, it's just kind of a straightforward slicing process. No particular reason. I'm going to do the slicing in this order. You'll notice, as promised, r and theta together and in the usual order. Notice that I have at the same time, I did anyway, write down r dz dr d theta all together all at once. As usual, it's just a matter of thinking about the slicing process. And, well, theta, that's what a theta slice looks like. You look at our domain, this upper half ball, this solid half ball sitting on top of the xy plane, goes all the way around. So theta is 0 to 2 pi. Everybody happy with that? Now we're going to restrict our attention to a particular given fixed theta slice, our theta slice, and you have to use geometric intuition here. This is what a theta slice looks like for an arbitrary theta, like one I have drawn here. Let's think about R. What do R slices look like? Well, R slices, constant value of R on this theta slice is going to look something like that. If you'd like, you can think of that as being how this green slice intersects with a cylinder representing a constant value of R. But we don't really need to think about that. So that's what an R slice looks like. And again, we can think about first and last. The first R slice is over here, where R is immediately seen to be 0. Right? Is everybody happy with that? Our upper bound for R, our last R slice, think about how these R slices move around. The last one's going to be there. Now, geometric intuition required to draw that conclusion, right? You got to see the picture. You got to use your intuition for what the shape looks like and see that point is that last R slice. And what do I know about that point? Well, I know various things about that point. One thing I know about it is a radius A away from the z-axis. Geometry. Right? That little red arrow that I drew there is a distance away from the z-axis. It's also a radius. The radius is given to be A, and so R2 is A. And then the last, just to finish this up, we're seconds away. For a given value of R and for a given value of theta, looking above that point, there's our z bounds. Z obviously starts at 0, and z ends at that point, which is on that surface, which has that equation. Again, make sure to always think this through. It's real easy to mess this up. We are looking for a z bound, so we solve this equation for z, and that gives our upper z bound right there. Okay, sorry I went over. I'll draw the line right here. We'll pick up here on Friday. Y'all have a good one. Don't forget about attendance.